Hello, everybody. So I'm going to finish up. We were looking at some trig integrals yesterday. We looked at ones that had powers of sine and cosine multiplied together, and we used this integral, or sorry, this identity here, the sine squared plus cosine squared is equal to 1. Let's actually make this a little bit bigger, I think. And so we're going to look now at a slightly different form, and we're going to use a related identity that we can actually derive straight from this one. If we divide everything in this by cosine squared, sine squared divided by cosine squared is equivalent to tangent squared. And cosine squared divided by cosine squared is 1. And 1 divided by cosine squared is secant squared x, right? Of course, sometimes cosine is 0 and we can't divide, but at all those places, this equation, tangent and secant, aren't defined as well. So this holds true for all the places where tangent and secant are defined. So this is really the same, or almost the same identity. You can see it comes straight from that. And we're going to use it when we're dealing with tangents and secants in our integrals. Now, I did several examples last time. I'm actually going to do one example and state the rule. And it's very similar to the other one, where you, depending on which one's odd and which one's even, you peel off one of your factors. So first, let's start with an example. Let's suppose, we'll start with this simple example. We want the antiderivative of secant to the 4th x dx. Right? So what we're going to do, and again, this is just something that is discovered by trial and error, really. And so there's not a huge mystery as to why we do this. I'm showing you this because it was shown to me, and it's a thing that works, right? I mean, this is not undiscoverable, but it would be discovered by playing around with these things the way a lot of things are discovered until something emerges. I think sometimes it just seems mysterious. Why in the world would you know to do this? You do things because you're stuck and you try to do something. So let's see why this will work. We're going to now use the identity that we just came up with over here and take this first secant squared and write it as tangent squared x plus 1. And then we've got secant squared x dx. Okay. And now we're going to make a substitution. I'm going to take the substitution u is equal to tangent of x. Du will be equal to secant squared x dx. Right? This is you can now sort of see where this is going. That this extra secant squared, we peeled off in the previous video when we were doing trig integrals with sines and cosine, we would peel off a single sine or a single cosine, a single factor of one of them, because then we would substitute the other one and get, so if you substituted sine, you get cosine. If u is equal to sine of x, du is cosine x dx, and vice versa. So we're peeling off single factors. Now we're peeling off squared because we get this tangent squared derivative is secant squared. So let's see what this does for us. This integral now becomes u squared plus 1 du, right? A fairly simple and straightforward 1/3 u cubed plus u plus c. And then we come back with our substitution thusly. So here's our antiderivative of secant to the 4th dx. Let's give it a try checking this. Let's take the derivative of what I just got. 1/3 tangent cubed x plus tangent of x plus c. The derivative of tangent cubed, we have to use a chain rule. So first we use the power rule. The 3 comes down. It's multiplied by 1/3, so those become a 1, and we're left with a tangent squared x times the derivative of tangent of x, which is secant squared x. And then we take the derivative of the second tangent, and we get, secant squared again. And again, And then the constant, of course, its derivative is 0. Again, this doesn't look like secant to the 4th, but if we play around with our, oops, that's not an equals. I'm factoring out a secant squared here, and I'm left with tangent squared x plus 1. I get secant squared x, and now using the identity that we've been using, this secant squared tangent squared plus 1 is equal to secant squared. This tangent squared x plus 1, we write as secant squared x. And then, of course, this is secant to the 4th x, which is what we thought it should be, right? So this, of course, is a very simple example. I will do, there'll be plenty of other videos with examples, but I just want to finish this one stating the rules. What we're looking at are, maybe instead of rules, I should call them, no, we can call them rules. I think these will always work. I wanted to call them suggestions because there's also times, let's just say it this way, integrals of the form, we want tangent to the mth power, secant to the nth power, right, where these are going to be positive integers, m and n. I'm calling them suggestions because if you see something that's not quite tangent to the mth power or secant to the nth power, these rules might work for them as well, right? So they're just kind of a good method to have in your head. When they're exactly in this form, great, we can just do it. As you see, the example I just did was actually not one of these, and I still used this process. So here's our cases. If n is even, so that means n equals 2k. And we're going to say that k is going to be greater than or equal to 2 in this case. So k is an integer, it's bigger than 2. If you just have a secant squared, you actually don't need to do anything except substitute u equals tangent, because you've already got that secant squared dx, right? If all you have is secant squared, you've already got this piece that we used up there. Okay. All right, so if this is the case, then you're going to take the tangent to the mth power x secant. So I'm just going to write it as to the 2k power x dx. And what you're going to do, you're going to take, let's see, what's the easiest way to write this? Let's peel off 2 powers of secant. So what will that be? Secant 2 to the k minus 1 x secant squared x dx. So there's a little bit of algebra in there. If I peel off 2 powers of secant, right, think of if 2k is an even number, right, so let's say it's 8. That's 2 times 4. 2 times 3 is now 6, so I'm 2 powers lower. I peeled them over here. And I can rewrite this as tangent to the mth power of x, the secant squared x to the k minus 1 secant squared x dx. And then we'll use u equals tangent of x. Okay? So again, there's a lot of this in this notation with all this indexing and keeping track of powers, but really it just means if you've got an even power of secant, peel 2 of them away. Oh, I forgot one step in here. Sorry, let's before we make our substitution, sorry, I'm going to add a line in here. We need to use our identity to make this 1 plus tangent squared x to the k minus 1 secant squared x dx. Okay, right, and now when you do the tangent substitution, du is equal to secant squared x dx. So now this du takes care of all of this, and then the u can replace these pieces. And so what you are left with is a polynomial in u that's an easy antiderivative, and then you substitute back what you started with, right? So again, it looks like there's a lot going on here, but it's just saying if you have even powers of secant, peel off 2 of them. What's left is going to be even powers of secant, which means you can use this substitution, 1 plus tangent squared, and then use a u sub, and you've got a polynomial, okay? Let's say if m is odd, we're going to use a very similar substitution. We're going to use tangent squared x equals secant squared x minus 1. So we're just taking secant squared x equals tangent squared x plus 1 and subtracting that 1 to the other side. Oops, why did I write plus 1 again? Okay, so again, basically the same identity, just a little algebraic manipulation. So if that's the case, we can write tangent. Since m is odd, I can write it as 2k plus 1. That's how we can write odd numbers where k is an integer. In this case, it's going to be a positive integer. Let's see, and we'll have secant n x dx. And so then we will peel off a single power of tangent. So now we'll have tangent to the 2k x, tangent x, and secant to the nth power of x dx. And we're also going to peel off a single secant power, okay? So I'm going to write secant here, and we're going to have 1 less power, and then we have, here's our extra power of secant that we peeled off, and I've got my power of tangent that I peeled off, okay? Now, we'll see where all this is going in just a second. This is, oh, let's rewrite this tangent before we go to the next step. This is tangent squared to the k power. So now we use that substitution. That tangent squared becomes secant squared x minus 1 to the k power. I have secant to the n minus 1 x secant x tangent x dx. And now we can use the substitution u is equal to secant of x, because du, the derivative of secant, is secant x tangent x, and then we move our dx over there, okay? And so then once you do this, du replaces all of this, u replaces all of these, and so again, we end up with a simple polynomial antiderivative, and then we have to reverse our substitution at the end, okay? All right, tons of notation here. I think this is good as a reference, but I think the best way to learn this is to try a few of them. What's going to happen is you're going to try to peel off the wrong thing. You're going to see that it doesn't quite work out the way you want. You go back and try the other one, okay? So take a look at these rules, try to apply it a few times, and I think pretty quickly you'll see what's happening here, right? I don't always remember these. If I haven't looked at these in a few months and I come up to a tangent secant antiderivative, I know that I got to peel one of them off, and I probably have to look at the identity and think it through for a few minutes before it registers which one I should do, or just try one. If it doesn't work, try the other one. Okay, that is it for this video. Like I said, there'll be lots of videos with examples as well, but this should get you started. All right, thanks everybody. See you next time.